Hello, everyone, and welcome to this latest webinar from IHS Markit titled Reconfigurable Compute for Secure Accelerated Networks. On the session today, our panel is going to explore architectural options and best practice for adopting programmable network hardware. The webinar today is co-presented by IHS Markit and our partner Napatech. My name is Joanne Emery. I'm the Associate Director for the webinar team in the IHS Markit Technology Group, and I want to first thank everyone for joining us. And just before we begin, I'm going to highlight some of the features that are available for you on the webinar and hopefully give you some ideas on how you can make the most of the experience today. So first of all, the webinar console that you're looking at is completely customizable. So you can open your own, open all the windows, close, move, resize, anything that you see that we have open on your screen, and you can arrange the console as you like. At the bottom of your audience console, you're going to see a number of application widgets, and these do contain some additional features that we've made available. So make sure you check these out during the webinar. One specific button I do want to call out is our resource list. This is where you can find a lot of additional material about today's topic. We do have a downloadable slide deck from the session today. We also have a number of case studies related to today's topic from Napatech. And finally, we do have a special report on reconfigurable compute authored by IHS Markit Senior Analyst Vladimir Galibov. All of these materials can be accessed and downloaded right from your console, so please take advantage of these resources. Also, we do want to make this an interactive session, so you're going to see a Twitter widget on the bottom of your screen. This means you can tweet directly from the console, and today we're using the hashtag ReconfigurableCompute. Also, we are going to have a live Q&A session with our panelists directly after the presentation. So please submit any questions or comments during the webinar, and we're going to try to get to as many of those as possible, so I advise you to get your questions in early. You see the Q&A box. It's right on the left side of your screen. You can use that anytime during the webinar. Also, if you do encounter any technical issues during the webinar, just click on the question mark widget, and you can get answers to any issues you have on the session. All right, so now let me introduce our panel. First of all, leading the discussion, we have Vladimir Galibov. Vlad is Senior Analyst in the Data Center Compute segment at IHS Markit. And joining Vlad, we have Daniel Joseph Barry. Danjo is Vice President of Strategy and Market Development at Napatech. And we're pleased to have both of them on the panel today. And now I'm going to turn the controls over to Vlad, and we'll get started. Vlad, to you.
Thank you, Joanne. Welcome, everyone, and thank you for joining us. Together with Danjo, we'll explore some very relevant industry trends. In fact, it seems rather fitting that in a week when server hacks make headlines, we explore network security through programmable adapters and look at how reconfigurable hardware in general can accelerate and secure the network. On the screen now, you can see our content and our agenda for today. Over the next hour, we will walk you through some of the high-level technological trends that have spurred the resurgence of reconfigurable compute, and we'll review some of the numbers that illustrate those trends. We'll then delve a bit deeper into the challenges enterprises face today and will face in the future. We won't only talk about problems, we'll also talk about solutions, and we'll even show you some of the success cases of reconfigurable compute deployments. Finally, Danjo will show us Napatech's approach to reconfigurable compute, and as Joanne mentioned, we'll have some time for Q&A. Let's start by reviewing our data center compute roadmap, which summarizes trends in servers and Ethernet adapters. If we take a step back and explore the 2014 to 15 timeframe, we see virtualization software drive up server utilization and connectivity bandwidth requirements. As we grow the number of VMs on a virtualized server, the impact is on networking as enterprises are running the equivalent of a small tall switch on each server. It should come as no surprise that that is the same time frame when offload Ethernet network adapters were born, from the prospects to free up CPU cycles by offloading network protocols and storage protocols to the NIC and adding a remote memory access that allows NICs to access in-memory data without CPU involvement. In the more recent time frame of 16 to 18, we've seen the demand on the network and the CPU continue to grow and spur the birth of programmable coprocessors and programmable Ethernet adapters. And here are a few factors as to why this acceleration of demand is happening. First, in 2016, we passed the halfway mark in terms of multi-tenancy. Now, most servers that ship will run virtualization or container software. We've also seen datasets such as those computed by analytics algorithms looking for patterns continue to grow, driving additional server connectivity requirements and demand for highly configured servers with more powerful CPUs, servers with more memory and more storage. And we've also seen the adoption of machine learning and artificial intelligence techniques ramp. And of course, there is enterprises' adoption of hybrid and multi-clouds, further fueling the need to automate and secure the DC network. As we look onto the next 2 years of the horizon, these drivers that I just mentioned continue to impact the market, and on top of that, IoT traffic further increases the demand for algorithmic offloads, where Ethernet adapters allow data to be processed in flight. We also expect to see CPU and coprocessors on a single silicon die in the same time frame. Finally, the limits of silicon are being reached as we move to the 5 nanometer wafer space and we try to go beyond. We see Ethernet adapter functionality expand to include specialized coprocessors and high-speed cross-connects to support deployments of large-scale compute clusters. We'll visualize some of those trends I just mentioned in the next slide, which will walk you through our server shipment forecast as well as our demand model for DC server compute. So to kick it off, we measure DC server compute demand by looking at a 20-year history of actual server shipments, data on multi-tenancy, including the penetration of virtualized servers and the number of VMs running and the growth of VMs running on each of those virtualized servers. We estimate the number of physical server equivalents and assign a computational value of those through our knowledge of CPU sockets per server, the performance of each CPU measured in SPECint, and the changes in the CPU roadmap over time. The total of that gives us DC server compute demand measured in SPECint. In this graph, the dark gray line highlights server shipments growth, and the red line highlights the growth in demand for DC server compute measured in SPECint. In the very first part of the horizon over there between 2003 and 2008, you see server shipments grow in parallel with compute demand. This is driven by the fact that the vast majority of servers are single-tenant. As multi-tenancy ramps from 2008 onwards, we start to better utilize servers, and as a result, do not need to ship an increased number of servers to satisfy a large acceleration in demand for the DC server compute that was fueled by the adoption of smartphones, tablets, and the software ecosystem around them. Then, as we move to the more recent timeline of 13 to 17, smartphones and tablet markets are saturating, decelerating the pull on DC server compute they create. And we continue to adopt multi-tenancy, continuing to utilize servers better and better, and thus not needing that many new servers. The result is that we're growing the number of servers in low single digits only. We can see that the dark gray line here in that part of the horizon is very close to zero if we zoomed in. So far, we're shipping less and less servers, but we're utilizing them more and more, with our connectivity bandwidth for each server growing. As we look forward, however, we see that the adoption of IoT and connected devices will shift the demand curve. If you add IoT and connected devices to the saturated population of smartphones and tablets, the growth curve moves upwards and shows acceleration. Coupled with the adoption of new software technologies like AI and ML, we see the growth of DC server compute demand accelerate. At the same time, multi-tenancy saturates. We already expect that it will pass the 70% mark in 2020. So with less utilization gains being possible, we need to ship more servers to satisfy the acceleration of demand. And earlier, I talked about datasets continuing to grow, fueling demand for highly configured servers with more powerful CPUs, more memory, and more storage. This has translated in an acceleration of server ASPs. And in this graph, the 8% server ASP growth in 2017 was largely driven by increases in the price of memory. But in 2018, we also see the effect of those data-intensive workloads. That has actually been a recurring theme of my conversations with the server vendors every quarter this year. In fact, we expect that while memory prices decline from 3Q18 onwards and through 2019, data-intensive workloads will maintain server ASPs over the $7,000 mark. I talked about the ramp of offload and programmable adapters as the compute demand grows and server users look at freeing up CPU cores, and here is a visual of our forecast. To set the scene, we define offload NIC as able to provide complete on-card processing of the network protocol, storage protocol, RDMA, etc. As I mentioned earlier, this technology started ramping in 2014 and has reached maturity, and we expect offload adapters to represent the majority of the DC Ethernet adapters sold in 2022. Programmable NICs have an onboard field customizable piece of silicon that can be configured and reconfigured by the end user. Within this horizon that I'm showing here, programmable adapters are growing the fastest, reaching 15% of Ethernet adapter ports and 33% of revenue in 2022. Initially, the majority of the programmable adapters were based on software programmable, ASIC, CPU, or SoC. And cost and ease of programmability acted as tailwinds to that type of programmable adapters. But lack of hardware adaptability over time, comparatively long design to deployment cycles, especially for the ASIC-based ones, and increasing number of cores needed to process packets at over 40 GE acted as headwinds to the growth of those ASIC, CPU, and SoC-based programmable adapters. With the transition to higher speed networks, we expect to see a ramp in adoption of programmable adapters with FPGAs. The FPGA on the adapter is composed of small generic logic blocks that can be configured and reconfigured with the application in mind. Here I mentioned some of the factors that are driving this forecast. In the companion report, you can actually see a detailed list. In short, processing data in flight for IoT, the rollout of carrier NFV, real-time AI, and security are all drivers for the growth of programmable adapters. Now, I'll pass you on to Dan Zhou, who will go into some of the trends I just highlighted in a bit more detail and the challenges that enterprises are facing. Dan Zhou?
Thanks very much, Vlad. So in an earlier slides that Vlad showed you, you could see that the demand for servers and computational power was first driven by multi-tenancy, but in the future it's going to be driven a lot more by the adoption of smartphones, tablets, and IoT. And this is the new industrial revolution that we're beginning to see in the networks around us. By 2020, we expect 8 billion people to be connected. We expect 52 billion devices, mainly IoT devices, to be connected. And that's going to be generating a large amount of data that has to be moved from the devices to the hyperscale cloud data centers that are supporting these services over what will be 5G mobile connectivity. But because we're looking at new types of services like smart cars, smart centers, and smart cities, we're also seeing a lot of new requirements, and this is going to drive new requirements for computing platforms going forward. So let's just take a look at some of those requirements now. Starting with 5G, you're definitely going to see in 5G some new requirements that we haven't seen before. We are definitely going to see some ultra-high speed and bandwidth requirements, and the goal is to have speeds which are 100 times faster than we have with 4G today. So high-speed internet access is definitely going to be a reality. 4K, 8K video streaming will be there, and smart city camera streaming as well. But we're also going to see a massive scale, unlike what we've seen before. We're going to see billions of connections from smart IoT devices, which will be coming and going. I mean, they'll be sending in data, and then you won't hear from them for a while. And so some of them will also be on the move. So that's going to cause some traffic patterns which we haven't seen before in the network. But one of the big requirements going forward is ultra-low latency. We're going to be looking at latency requirements which are 50 times lower than we're seeing today. And that's because of these critical services like autonomous vehicles, e-health, and industrial automation, which will require this kind of latency going forward. So these are some new requirements that we have not seen before. If we then look at what that's doing to how we're architecting the networks, it's actually forcing compute to move closer to the edge. Lower latency in particular is something that's going to be driving compute closer to the edge, as we want to make sure that we're providing high bandwidth and efficiency and low latency to some of those new services. So if you just imagine autonomous vehicles, for example, you know, they're going to be driving from one cell to the next, and we're going to have a lot of new, smaller cells in 5G. So we're going to see having to support that service, moving the connectivity from one cloud edge to the next. So we're going to have a very dynamic network going forward. That's also going to mean that workloads are going to be moving from the core to the edge and between the edges in a much more dynamic way than we've seen in the past. So SDN and NFV or similar type of solutions are going to be critical to 5G, and as well as network slicing and these things to ensure that each one of these services get exactly the quality that they deserve. But there is also a couple of other things here that are a consequence of this that we need to be aware of from a compute hardware point of view. The first is that if we're moving computing closer to the edge, we're going to face some constraints on how much we can do in that confined space at the edge. So some of the solutions that we have in the core may not be possible to do at the edge. For example, in the core, if you need to scale a service on demand, you just add more servers, right? But that's not just going to, you're not going to be able to just put more servers into the cloud edge. It's a confined environment. So there'll be a need for compute solutions there which are much higher performance and efficiency in smaller space with more power constraints, etc., that you have than you have in the hyperscale data centers today. But in the hyperscale data centers, we're also going to see new demands because the networks, as we've seen, to support these different types of services are going to have to be much more agile and flexible than they are today. This is where SD&V comes in. Well, SD&V can only be as agile and flexible as the network that's supporting it and the data center that's supporting it. So there is going to be a demand for those compute platforms to be able to adapt with the same kind of agility and flexibility of the software that's controlling it and the services that are using it. Now, another major concern of all this, of course, as well, is that we're going to have a lot of IoT devices that might be privately owned accessing the network. So it's going to be outside of the control of the service providers. So that means that security has to be top of mind, which it is for enterprises, governments, and all sorts of organizations all over the world. But one of the concerns that there is in the security area right now is that the security teams themselves are actually overwhelmed. So this is just some data from different sources that I'm presenting here to you, showing that security teams are seeing more sophisticated attacks and more of them. Actually, a 27.4% increase was noted in 2017 on an annual basis. But the networks themselves are also getting more sophisticated, as noted here, where you can see that 57% of the enterprises surveyed by IHS Markit were showing a mix of on-premise and managed security services using up to 11 different cloud service providers. So what you're seeing here now is that you have security teams that have to deal with more sophisticated attacks, more of them, in much more complicated environments, which are spread over different geographic areas, even the cloud. So that's going to be putting its own pressure on the security team to keep up. But to add to that, we're also seeing that the teams themselves are feeling overwhelmed by the amount of information they have to triage. So you are going to be getting a number of different security alerts from different security devices and other sources from different parts of the network and from the cloud that you have to make sense of in a real-time basis to see, am I under attack or am I not under attack, or where is it coming from? And already in December 2016, 93% of the surveyed organizations felt that they were already overwhelmed then. So there is absolutely a case to be made to say that going forward, this is not going to get any better as we head into this cloud mobile IoT future. So security has to be top of mind when we're designing these solutions. So if we look at this and gather it all together, you can see that the compute platform to the future has to meet multiple demands, and some of them are uniquely new. Providing a cost-efficient performance is kind of bread and butter for any sort of device going into these locations. So we expect that to be the case. But if we look at some of the other requirements, like supporting massive scale, standard servers are the building block of hyperscale data centers today, and they've made scale possible. But the question is, can that kind of approach be replicated at the edge? And that's an open question, to be quite honest. We believe that there's going to be a need for new types of compute platforms which are tailored to the requirements of the edge. Then if you look at the bandwidth requirements, as Vlad alluded to earlier, standard servers are starting to struggle to provide the performance that's required. This is one of the reasons you're seeing the growth in offload and programmable NICs. And we're going to talk a little bit more about that later. So already here we have some concerns about how we're going to meet these demands. But if you start looking at the new demands that have been introduced, like executing with ultra-low latency, embedding security capabilities, and adapting at the speed of software, these are all new requirements for more agile infrastructures that we haven't seen before and are going to pose a new challenge for compute platforms. So having looked at that, I think it might be time now to hand back to Vlad and have our first poll question of the day.
Thanks, Danjo. Now we'd like to hand over the power to our listeners, and we would like to ask you, have you or are you planning to deploy reconfigurable compute in programmable Ethernet adapter form, or if you are deploying already FPGA on motherboard, that would also work in your organization. And your options are, I've already deployed in production reconfigurable compute, I'll deploy in 6 to 12 months, I'll deploy in 1 to 2 years, no, or I don't know. And while I give you a moment to take a look at the question and answer, I also want to remind you that we are ready for your questions for the very end. I can see that some questions have come in, but I just want to remind you to keep sending those questions in, because it looks like we will have quite a bit of time to answer them in the end. So I will move on and show you our actual survey that we ran with North American enterprises, while the numbers get crunched into our into our number cruncher for the poll, and then we'll take a look at your answers in a second. So I hope everyone's had a chance to answer, and I will move on onto the solution space. So far we've talked quite a bit about some of the challenges that have happened in the market, some of the changes, the market dynamics that have happened, and really the increasing demand that is happening on the compute platforms and on the network. And now we're going to talk about some solutions. So we at IHS Markit do survey quite a lot of end users, both both enterprises and service providers. And what I'm showing you now is a survey of 151 North American enterprises All of these have a data center, and all of these have over 100 employees. About half of the respondents are from what you could call a small or medium enterprise on average of 455 employees, and the other half are from larger enterprises on average with over 15,000 employees. And we asked them in what percentage of their servers they run the following type of offloads or programmable NICs. The data shows some very key trends. First, enterprises are moving away from network protocol offloads. You can see that respondents are planning to actually adopt less network protocol offloads in 2019 compared to now. And what they're actually doing is they're looking to adopt different workloads. For example, to invest in data plane offload or to invest in storage protocol offload. So there is the diversity of demand in the network is increasing. And this diversity on demand of the demand is creating uncertainty, and we're not surprised to see enterprises plan to increase the use of programmable NICs. The fact that FPGA-based programmable adapters can be reconfigured as the demand of the network changes, you can push a new rule for processing of a different offload, is an investment driver. Actually, when we asked the similar question to service providers, both telco and cloud, they answered with a similar response. The need to process higher number of packets and implement new security measures is a further fuel for the use of programmable adapters. And I'll show you some further data in a moment, but you can see here that investment in programmable adapters is growing from 15 to 16% of servers by 2019. And in fact, this number was actually higher when we asked the same question to service providers. And we also see a significant surge in algorithmic offloads. We actually expect programmable adapters to be used for some of those algorithmic offloads. So this growth of 8 to 13% of algorithmic is actually also correlated to programmable NICs. So let's take a look then on how you answered that question. I can see that about 19% of you have already deployed reconfigurable compute in production. This is actually quite in line with the trend that we just saw of North American enterprises. So we can see that we're in the high teens of deployment in terms of reconfigurable compute. It seems like no one is looking to deploy in the 6 to 12 months, but you are looking to deploy in the next 1 to 2 years. We can see that a small number of respondents are not looking to deploy, but there is a very large number of people who don't know if that's the right solution for them. And I think this is the perfect setting stone for us to take a look at some of the actual use cases and benefits of reconfigurable compute. So I'm going to pass you on to Dan Zhou, who's going to take us to the solution space now. Dan Zhou?
Sorry about that. Yes, I'm sorry. I hope you can hear me now. So if we look at reconfigurable computing platforms, they're basically standard servers with, in one type of solution, FPGAs introduced in the server. As you've seen from the previous surveys that were done there, there's a large interest in offloading different applications now onto FPGAs. And one of the reasons for this is the depth of Moore's Law, basically. It's getting harder and harder to keep up with Moore's Law using CPU technology. And that's causing standard servers to struggle to keep up with processing demands, which is driving the need for these offload and programmable adapters. So one of the solutions is to combine FPGAs and CPUs in the same standard server. And the preferred format for doing that this year, at this point, is FPGA-based smart NICs. So basically, you're replacing the standard NIC in a standard server with an FPGA-based smart NIC. But what we're also going to see is this FPGA technology being embedded in the CPU, and there's already examples of that out there, and potentially also on the motherboards of the servers going forward. And the expectation is that we can actually close the performance gap between the increased needs that we can see are going to come from the cloud mobile IoT future and what we can provide from standard servers. So for those who are not familiar with FPGAs, I'm just going to give a quick introduction to what an FPGA is and how it differs from CPUs and how you can use a combination of CPUs and FPGAs to actually get an overall better performance on standard servers. So if you look at the way a CPU works, basically what it does is it divides its time between all of the different applications and processes that need to be run on it. So that could be hosting websites or processing e-commerce transactions or whatever it might be. But what happens is if you have a very heavy workload like encrypting data, which is very intensive, and for which a CPU isn't ideal to do, you're going to see a couple of things happening. First, the encrypting the data process itself, since the CPU isn't ideal for that, it's going to take some time. And that means that the other processes are going to have to wait until that process is complete. And as speeds and data increase, this effect just gets even worse. So maybe the encryption of the data itself might have to wait because some other processes are being done. But in general, you're going to see all of the applications that are running on that server suffer. So the idea is to combine the CPU with an FPGA so that you can offload these very intensive tasks to the FPGA, which is a far better platform for these kind of algorithmic workloads. So by doing that, you have a double effect. One is that the encryption of the data is performed much better on the FPGA because you can parallelize that particular algorithm and get much better performance out of it. But the other thing is that all the other processes that are using that standard server won't be delayed and they'll get the maximum power out of the CPU. So the overall system performance is improved with the combination of these two technologies. Encryption is just one example of a task that can be done here. There are many other examples that we'll see soon, like compression, video transcoding, and other things. But it's really the combination of the two which brings the best of both worlds to bear on the performance issue. Another way that FPGAs differ, which Vlad mentioned a little bit earlier, is in the reconfigurability of the hardware itself. So if you look at CPUs or even GPUs for that matter, basically those are static ASIC chips. So they have certain capabilities. They have a number of cores that are available, but that's the static configuration. The data paths are all static. All the things are already defined. The data paths are defined. So you really have to work within the confines of what that provides to you. And in many cases, there's a number of software applications which will be vying for the attention of that ASIC chip through the software operating system and scheduler. So the reconfigurability is really in the software where you can have different instructions that can be processed on the CPU, the GPUs. But the issue is actually guaranteeing performance and low latency with this because, especially if you take an example of a GPU, what you're going to see is that there's a number of actions that can be defined on different cores to be performed on data packets. But depending on what kind of packet is coming in and how many actions have to be performed on that, you're going to see different timings for how long it takes to actually process that packet. So you're going to see a very non-deterministic performance in this kind of ASIC when you're doing that. And that gives some low latency problems because you can't guarantee that the latency is going to be low. And you can't guarantee performance either. So this is one of the drawbacks of using that. Very high performance still, but not guaranteed, not deterministic, and low latency is an issue. So the reason why FPGAs are very exciting for a lot of people who are working with them is because of the fact, as Vlad mentioned earlier, it's basically some logical blocks and that can be combined. And that combination is defined using a software file called an FPGA image. So by using this FPGA image file, you can actually define exactly the data path that you want your packets to take as they go through this FPGA. So you can actually tailor the data path exactly to your needs. And this is one of the things that's been very attractive with FPGAs going back, because You could also have non-standard data paths. You could have different sizes of registers. You can do things that are absolutely customized to whatever you're trying to achieve. So you can really have an FPGA image that is tailored to the software application. And you can change out these FPGA images real time, on the fly. So as the new software application is coming on board, you can actually change the FPGA image so you can fit the needs of that software application. And the good news is that because you've tailored this data path, it's set in the FPGA and it's the same for all packets. So you're going to get deterministic performance no matter the load, no matter how much has to be done on each individual packet. So you're getting a very deterministic solution, and you can make a very low latency solution, which is perfect for the applications that we've been talking about earlier. So this looks like a very good platform for some of those requirements that we were talking about, especially low latency and high speed. And the first adopters of this kind of approach were cloud service providers, and Microsoft Azure in particular. So back in 2015 timeframe, they built their own smart NIC with an FPGA on board, and they have now deployed that across all of their data centers, supporting services like Bing and Microsoft 365. And they've been very public in talking about the benefits that they've been able to achieve, the performance they've been able to achieve using that. So that's had a knock-on effect in the industry. It really opened the eyes of a lot of people to what could be achieved using this kind of technology combination. So Intel, which is the largest provider of CPUs and really is the backbone of the data center today, they acquired Altera, the second largest FPGA vendor in the world, for a record sum at the time of $16.7 billion. And this is partly because of that Moore's Law issue we were talking about earlier, that if you want to continue to deliver performance improvements on a regular basis, then you need to combine CPU technology with something like FPGAs in order to do that. And they're already embedding FPGAs in the CPUs, with CPUs, to actually achieve that. So that's a space that's very interesting. But we've also seen Amazon Web Services, Alibaba, Tencent, Baidu, and Huawei introducing FPGA-based solutions, FPGA as a service, cloud server platforms for this space. So there's no doubt that these guys are the ones who are leading the pack when it comes to adoption of reconfigurable computing. But if we look at why they're doing that, I mean, this is just showing some results that Microsoft presented earlier this year at NSDI, showing their throughput and latency compared to competitors like AWS and others. And you can clearly see they're the blue lines on this graph, and you can clearly see they're getting better throughput and better latency for their services by using this approach. And if you combine that feedback with some figures here from Xilinx, who is the largest FPGA vendor in the world, you can see that FPGAs provide not just a little bit of better performance, but magnitudes different in performance for different types of applications, like machine learning inference, 11 times better performance compared to server CPUs, 33 times better for data analytics, SQL queries, video processing, storage compression, virtual switching, So there's definitely a whole range of applications here which are benefiting from offloading to FPGAs. Now, there's a number of different areas where this can be applied. We at Napatech are very focused on security and networking, which are central to that cloud mobile IoT future that we're talking about there. But it's not just about telecom. I mean, the enterprises, governments, our data centers, they can all benefit from these technologies also. So at this point, I just want to hand back to Vlad to go through some data that IHS Markit has got over the last year. Handing back to you, Vlad.
Thanks, Danjo. And this is some of the follow-up questions that we asked the North American enterprises that I showed you their response earlier, the 150 North American enterprises that we surveyed earlier this year. And when we asked them why they're deploying programmable NICs and the workloads that they're using them for, we saw that security is very much at the forefront. And actually, they had told us in the same survey earlier that they are increasing their investment in security, and we can see that one of their investment is going towards the programmable NIC. And firewall and NAT and encryption and decryption are incredibly processor intensive, so prioritizing co-processing for security application is not at all surprising. Respondents want to avoid increased security-related computation, taking additional CPU cycles, and recognize it is best to enforce security at the server within the network, i.e. the NIC, rather than on the CPU. And you will be able to also see this in the companion report. So at this point, I would like to actually see, and I'm sure you want to see, some real-life deployments. So I'll hand it back to Dan Zhou, who will show us some of the actual use cases that Napatech has already seen.
Yeah, thanks, Vlad. So I'm going to go through 4 use cases just to show you the breadth of application of this technology. So Napatech has been around for 15 years, and we've been working with what we could call reconfigurable computing for that entire time. So we've been working mainly in the areas of security and network performance management, and now we're just seeing a lot of other applications starting to have the same needs that we saw already back in 2003 for these applications. And just to give you 2 examples of how we're using that today, one from IBM. And their security information and event management solution, where they need to, the way a CM works is it actually compares the information that it's getting from different security platforms about what's going on from a security point of view with what's actually going on in the network. And with very good network information, they can actually help with false positives that are coming from the security devices, but also maybe detect things that are happening in the network that could indicate that those security defenses have been breached. So it's a very important part of that security stance. So they're using reconfigurable computing and Napatech SmartNICs in this regard in their Qflow collectors, which are actually looking at network data. They're doing packet capture, as it's called, where they're actually looking at all the data in the network. And the part of the job that we're doing is to make sure that that data is provided in a way to the CM solution so that it's easy to extract all the information and get deep insight into what's happening in the network in a very fast way. And speeds up to 40 gigabits per second. Something similar to that for network performance management is what we're doing at Neusoft in China. Here, one of the unique requirements is the scale of the solution, where it has to scale to millions of simultaneous users. And again, what we're doing here is looking at the network data and being able to do that at very, very high speeds, and then provide that back into the real-time analysis platforms that can compare what's happening in the network with what's actually happening in the application servers. So here it's about data capture, large amounts of data being captured at very, very high speeds with very, very low latency. Now, if we come into the NFV space and some of the more future-looking things that we're doing, we talked earlier about the need for compression and particularly encryption for security offload and these type of applications. And we've got a couple of examples of that. First with Nokia, where one of the things we needed to do there was to help Nokia to compress files, gzip compress files at 40 gigabits per second. Now, when you try to do this with in software, it takes about 40 CPU cores to do this, because each CPU can handle about 1 gigabit per second of data. But by offloading that into the SmartNIC and the FPGA in the SmartNIC, you can actually reduce that number of CPU cores to 1, and you can actually do the compression 30 times faster than you can do it in software. So it's a very, very powerful solution. Something similar is a demo that we've been doing this year with China Mobile, Lenovo, Xilinx, Radisys, and Xilinx Inside about 5G virtual RAN acceleration. And here we're looking at the virtual eNode B and accelerating the PDCP protocol, which as part of the protocol it has there is encryption, IPsec encryption using ZUK that has to be done. And using a software solution, it was possible to get 1 gigabit per second throughput. But by actually offloading these pieces like the IPsec and parts of the PDCP protocol onto the SmartNIC, we're able to achieve 10 times performance improvement. In other words, 10 gigabits per second going through the SmartNIC. So you can see the power of these solutions here, you know, and we have actually use cases that are available in the resource section that you can download to get more information about this. That gives you an idea of the kind of things that you can do and the breadth of applications that you can do with this kind of technology. So if you look at Napatech's approach, I want to give a couple of slides on that just to explain where we're coming from. So we wouldn't consider ourselves a SmartNIC vendor, at least not from as a SmartNIC-centric approach. We have something we call the Napatech Recofigurable computing platform, which is a combination of hardware and software, but it's very much application-driven. So as you mentioned earlier, one of the advantages of FPGAs is that you can actually tailor the FPGA to the needs of the particular application that you need to support. And we have a lot of data out there on things we've done with Bro, Wireshark, Suricata, Snort, T-Rex, working with companies like NTOP, which is very familiar to people in these communities with their PF Ring solution, and to Disk and other types of open source solutions that they're providing, just showing the performance improvements that you can achieve by using reconfigurable computing and FPGA-based SmartNICs. So everything starts with the application and understanding what the needs of the application are. But it's very much a software-focused solution. I mean, as we showed earlier, the way that you configure the FPGA is through software, is through FPGA image files, and then there's the driver and the interfacing software that goes around that to make it easy for the application to use. And there are some areas where we've packaged that together so it actually fits to certain types of applications. For example, capture applications. We saw two examples in the use cases earlier with IBM and Neusoft of that kind of application where you're just capturing information off the network and making it available for analysis in a very efficient way. A variant of that is inline, where you're actually getting information off the network and processing it in real time with very low latency, but also retransmitting that back out onto the network. And then you've different types again with virtual switching. So OVS acceleration in NFV environments, for example. So these are all very different ways, different types of software solutions that you can actually put onto the same SmartNIC hardware. We have a full portfolio of SmartNICs that we've been offering all through our existence. But we also want to ensure that any solution that we make is hardware independent. So we can support different form factors like SmartNICs or smart cards, which don't have network ports on them, are mainly co-processors for things like the Nokia 40 gigabits per second file compression. But also preparing for the future where we'll have FPGAs in CPUs. That's also going to be part of the solution. And that, of course, then allows us also to support other vendors' hardware, if that's a requirement going forward, and also to be able to place this in many different locations in the network. So these are all very important attributes. So it's application-driven, software-focused, hardware-independent, and for the entire network. This is for the approach that we're taking. And we have a lot of experience in how you actually get the most out of standard servers. So we have a lot of features that we've already built into our SmartNICs and that we can bring to bear in some of the solutions that we have. You know, like zero packet loss for packet capture applications, very precise time stamping in hardware, which is a picosecond level, which is also very important for many applications. But also a lot of things that we've done which ensure optimal performance in a standard server, where we're using our knowledge of the architecture of servers to provide a good solution, like NUMA balancing and intelligent multi-CPU distribution, burst buffering to ensure that we're not losing any information, but also things like optimal cache utilization to have a faster data delivery to the applications that are on the server. So there's a number of different things that we've developed over the years which we're bringing to bear in these solutions that we're delivering. And it's all through a single API that allows the customer to make one development that will support multiple solutions, because you can run this on different kinds of hardware with different speeds, different port configurations. So a very versatile solution that we can offer. But this one, I just want to hand back to Vlad for some conclusions on what we've seen today.
Thank you, Dan. And I want to remind everyone that we will soon run a Q&A. So do check that Q&A panel on the bottom and do let us know if you have any questions. So to summarize our discussion today, we started by showing you that we did show you that enterprises and service providers are adopting programmable NICs in the survey data there, and again you'll see this in the companion report. We've already seen that the CPU alone cannot satisfy the growing data server compute demand, or we can see that the CPU generations are not really managing to come in fast enough, and even if we were following Moore's law, probably would not be as fast as the demand acceleration that we're seeing. The new software has ramped server connectivity bandwidth requirements already, and we expect that this trend will only accelerate in the future. Our workloads are growing in diversity. We can see that that enterprises and cloud and service providers will be deploying different and more diverse workloads in the future, which really does highlight the need for reconfigurable hardware, something Microsoft was particularly passionate about recently. IoT traffic is increasing algorithmic offload demand for processing data in flight, something that I'm sure wouldn't surprise anyone. It would be impossible to move all of the data we collect at the edge to the cloud for processing there. And finally, programmable adapters are well suited for security applications. In fact, hardware security is something that people have talked for a while, but seeing as now we're seeing hardware hacks, addressing them with hardware security, with hardware-based security seems fitting. So at this point, I will pass you on to Joanne, who will just remind us about the Q&A.
Great. Thank you, Vlad. A very good discussion here. So just a reminder to everyone here, the Q&A is starting now, so send your questions in. Also, just one more reminder, if you do want to download a version of the deck, it is available in the Resource Center along with that special report, so check that out. Now I'm going to turn it back to our experts, so Dan, Joe, and Vlad, let's get started with some of these questions.
Thanks, Joanne. And I do have a few first questions here that are quite interesting, and I hope that I can ask you, Dan, Joe, to let us know what you think from your perspective. And the first question is quite related to something that we covered earlier. We have seen that there has been the growth and discussion of both programmable adapters and programmable coprocessors, and we've seen different technology in those. When is an FPGA better than a GPU for accelerating workloads?
Yeah, that's a really good question. That is. So many will know that GPUs from NVIDIA, for example, have been used for a long time in high-performance computing and things like this for actually performing some of those algorithmic accelerations. And in that regard, FPGAs and GPUs are very similar. If the algorithm can be parallelized, then you can put it on an FPGA and a GPU and actually achieve performance acceleration. But some of the issues that people run into when they're trying to do things on GPUs are some of the things I just talked about earlier. If you have applications which are latency sensitive and need very deterministic performance, then GPUs can be a bit of a concern in that regard, especially as you go into higher speeds, which I think you talked about earlier as well. So that's one of the big concerns there. The other concern is power. So you tend to get some very power-hungry solutions out there, which often also come with form factors which can be quite large, like full-length cards, full-height cards. This is good for high-performance computing and maybe good inside the data center, but when we start looking at the requirements at the edge, this could be a bit of a concern because there the space environment that you have is not going to be great. And to add to that, then, I mean, the traditional answer is that, FPGAs are, because they're so configurable and you can have exactly the data path that you want, then you don't have to work within the constraints of what the what the GPU actually provides you with respect to data paths, register links, etc. So you can actually tailor that to exactly what you want. And I think that's become some of the appeal of FPGAs as well. So FPGAs do have many of the same advantages as GPU, but a lot of other advantages that are difficult for the GPUs to actually meet.
Thank you, Danjo. And you know, when we talk about deploying reconfigurable computing, where do you think it's likely for us to see it first? At the core or at the edge?
Yeah, that's another good question. So we've seen use cases in every area. So we've seen them at the edge, we've seen them at the core. And if you look at Xilinx and Intel, they have a lot of different examples in many, many different areas. But when you think about what we went through today, I mean, it seems logical that the area which would benefit the most from reconfigurable computing would actually be the edge. It's here where you have a lot of those requirements and constraints that make reconfigurable computing a no-brainer. Low latency requirements, as we talked about earlier, very difficult to achieve with other types of technologies. The ability to provide high performance with very small space and at low power, or relatively low power, should we say. That's also another advantage that you can see from reconfigurable computing. And of course, these environments are getting very dynamic, so the ability to be able to change what the hardware is doing on the fly using different FPGA images is also a great advantage. So definitely, I would think that at the edge would seem to be where this would have the most impact and would be the most logical place to start.
Thanks. And another interesting question here in relation to some of the materials that we showed. On slide 17 earlier, in general, through the conversation, we said that we showed a programmable NIC being used in a server, and we showed 3 deployments. One has a motherboard with FPGA and CPU with FPGA. Does this mean that we have to change motherboard and CPU to use a programmable NIC? Is the first question, and there is a follow-up.
Oh, right, I understand. Right. So that was an effort to just show that there are different ways that the FPGA technology could be introduced into a server. The norm today is FPGA-based smart NICs. So that's as simple as taking the standard NIC that's installed in the server and replacing that with a smart NIC with an FPGA on board. So this is so that's the first thing. But what we are seeing is that you're going to see new CPU chips coming out with FPGAs embedded. I think Intel's been quite public about that in their ambitions in that area. So that will be new servers with this capability on board, right? And then there's the potential for FPGAs to be delivered on the motherboard. So that's something that's still being planned, but it's not. It could well be something that we'll see in the future. So for those 2 final examples, yeah, you'd see new types of servers being introduced. But watch this space. I mean, these requirements that we've been talking about during the presentation will require new compute platforms and new types of servers as well. The SmartNIC FPGA approach helps you to take existing servers and turn them into reconfigurable computing platforms, which is quite appealing. But I think we'll see a lot of evolution in server architectures as well going forward to accommodate these kind of technologies.
So do you think that FPGA on motherboard will decrease the use of programmable NIC? And before you answer, I'm just going to give my perspective. As an analyst, we research multiple areas of programmable compute, and we can definitely see that some workloads are using one type of programmable or reconfigurable compute solution, while others use others. So we've seen, for example, some parallel compute related workloads that are not related to moving data outside of the server being done on a coprocessor, while others that are doing FPGA-based adapters that are doing processing on the packets are using an adapter. But do you think that we'll see then a decrease of programmable NICs yourself, Danjo, if we start using FPGAs on motherboard, for example?
It's hard to know because if you're starting to get to the point where you're putting FPGAs on the motherboard as standard, then there's a lot of offloading going on then and a lot of processing going on in FPGAs. So you're going to see different footprints available. It depends on how big the FPGA on the motherboard is, right? If it's very big, then it can support a lot of different applications on that. And that's always a cost trade-off when you're doing that. I could imagine that you would see a potential combination because for some networking activities, it could be very good to have a smart NIC where it's being very processed very close to the ports. So there's certain things that you may want to filter right there at the port and not send up into the server. So you want to keep that clean. You could potentially have that filtering happening on the motherboard as well, of course. But I think that there might be applications that will require something that's very close to the network port. And then there's the co-processing, as you were just mentioning there. So you have some co-processing that will be done on the CPU, but there would be a good case for saying that the FPGA on the motherboard would be the most likely candidate for doing co-processing algorithmic offloads. So you could probably see a combination of network offloading happening on a smart NIC while you'd have co-processing happening on the motherboard or on the actual CPU itself. So, but it's early days. You never know what could be the combinations going forward.
Thank you, Danjo. And we are out of time. I will just remind you to tweet us any further question. There is one question on security that we haven't answered. I will tweet an answer to that question after the session. So now I'll pass you on to Joanne for some to close us off. Thank you.
Great, thanks, Vlad, and thank you to Danjo and of course the whole Napatech team. I want to thank both our presenters for a great session today. As Vlad mentioned, there are some questions. If you didn't hear your questions answered, we will reach out directly with some answers to that. Just a reminder to everyone here, the webcast will be available on demand at the close of this session. You can use the same link you used to get in before to access this afterwards. We encourage you to share this with any of your colleagues that you think would be interested in learning more about reconfigurable compute. And we want to thank everyone for joining us today. We hope to see you again on future IHS Market webinars, and have a great rest of your day. Thank you very much.